So let's take a look at our first product of sums K-map example. So just like sum of products, we can go from truth table to K-map or shorthand notation to K-map. So in this case, we're looking at our truth table. And just like sum of products, it can be handy to number our rows in our truth table and number our cells in our K-map. So let's actually start off by doing that. So we'll do this nice. How about that green? And so we'll say, right, we already start at 0, 1, 2, 3, 4, 5, 6, and 7. And nothing changes here, right? It's still 0, 1, 2, 3, 4, 5, 6, and 7. And now that we've done that, it's pretty easy to just go from the truth table to the cell. So we know we've got 0, 1, 0, 1, and all the rest are zeros. Perfect. Now, what we want to do in product of sums is we want to play the same Karnaugh map game when we're trying to get essential prime implicants, or the biggest possible implicants. But in this case, we're making our implicants around the zeros. So it's still the same game where we just can kind of pick a seed. We start here and we say, oh, that can actually grow a little bigger. We could get this one and we say, oh, that could grow even bigger. And we can get this whole guy here. And then we look at zeros that aren't covered by any implicants. So we could start here and we could say, oh, okay, this could get bigger. Could get bigger. Nope, we can get biggest to this day right here. And then we can go through and say, hey, do we have any distinguished zero cells in this case? Distinguished zero cells are just zeros that are only covered by one implicant. So that's here, 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 and here. And so since this implicant, this prime implicant, has distinguished zeros in it, that means this is an essential prime implicant. Same as this one here. So that means that we've covered it using only essential prime implicants. And that means that we're done. And now we want to write our function for x. So this guy's term is, well, it looks like it's a function of just, well, we still play the game where we see what stays constant. And in this one, it looks like c stays constant as a 0, a constant 0. So just like how we represent our canonical product of sums functions, if the variable is a 0 for that state, if it's a 0, we do not knot it. We only knot it if it's a 1. So in this case, we have c, just c. And here, so that's actually the only thing that stays the same for this term. And then we've got this term here. And the only thing that changes, or the only thing that stays the same, sorry, is a. A stays the same and it stays as a constant 1. So we're going to put a here. And since it's staying as a 1, remember it's kind of the opposite of sum of products, where we have to knot it if it's a 1. So each one of these terms is only represented by one variable, right? One kind of literal there. And so our product of sums, right, the name is product of sums, meaning that we've got some things that are ORed together, in which case we don't really have anything ORed together because they're all just one variable terms. But then we have a product, meaning that we AND them together. So that means we've got C and A prime. And there we go. That's our function for this problem.